All right, welcome. Today we are going to break down a mathematical idea that sounds kind of fancy but is actually super simple and honestly really powerful, the convex cone. I know, it might sound a little intimidating, but I promise you, by the end of this, you'll see it's all built on just a couple of basic rules.
So let's just jump right in with the big question. We've all heard of a cone, right? But what's this convex part all about? What's the secret sauce that takes a regular old cone and transforms it into a convex cone? Well, that's exactly the mystery we're going to solve together.
And here's the best part. You can put away your heavy textbooks because this whole concept, this entire idea, is built on just two simple rules. Once we get these, everything else is just going to click right into place.
Okay, so to get started, let's forget about math for just a second. I want you to picture a flashlight. You're in a dark room, you flick it on, and this beam of light just shoots out. It starts from one single point, let's call that the origin, and it just goes on forever in a straight line. That beam, that single infinite ray of light, that's it. That's the simplest cone you can possibly imagine.
Okay, so now for the official math speak. The definition from our source calls this a linear cone, and it says it's closed under positive scalar multiplication. Whoa, that sounds like a mouthful, right? But all it really means is this. If you have an arrow, a vector, that's in your cone, you can stretch it to be twice as long or shrink it to be half as long. You can multiply it by any positive number you want, and that new resized arrow is still part of the cone. It's still pointing in the exact same direction.
So this is it. This is our first big idea, the foundation for any kind of mathematical cone. We're just going to call it the stretching rule. It's what gives a cone that infinite ray-like quality we were just talking about.
And this slide basically gives us a super simple recipe to build one. Step 1, start at a single point, the origin. Easy enough. Step 2, pick a direction, any direction you want. That gives you your starting arrow. Step 3, apply our new stretching rule. You can make that arrow longer or shorter by any positive amount. And finally, step 4, once you gather up all those possible stretches, boom, you've got a single infinite ray. And that's your most basic linear cone.
Okay, but a single ray is, a little lonely. What if you have two rays, or a bunch of them? Well, to get from a simple linear cone to a much more useful convex cone, we just need to add one more rule to our recipe. And believe me, this one is a total game changer.
So here it is, our second rule. It has to be closed under addition. What does that mean? It means you can grab any two arrows from inside your cone, add them together tip to tail, and the new arrow you get, the result, is guaranteed to land right back inside the cone. It's not just about stretching one arrow anymore. Now it's about combining them. No matter how you mix and match them, you can't escape the cone.
And this slide just lays it all out perfectly. A linear cone? It just has to follow the stretching rule. So you can have a bunch of separate rays that have nothing to do with each other. But a convex cone, it has to follow the stretching rule and the new adding rule. And that adding rule is what does all the magic. It's what forces all the space between the rays to get filled in, creating one solid connected shape.
All right, enough theory. I think it's time to actually see what this looks like. We're going to look at a couple of examples straight from the source material that will put these two rules to the test and make this whole distinction crystal clear.
Okay, so look at this. Imagine you just have two separate rays, both starting from the origin, but pointing in different directions. Now, this is a cone, technically. Why? Because it follows our first rule, the stretching rule. You can pick any point on either ray, stretch it, and it stays on its ray. But it completely fails our second rule. If you take an arrow from the first ray and you add it to an arrow from the second ray, where do you end up? Bam! You land right in that empty space between them. Since you landed outside the set, it is not a convex cone.
Now look at this one. It's totally filled in, kind of like a slice of pizza that goes on forever. This, right here, is a proper convex cone. Why? Because it follows both our rules. You can take any arrow inside, stretch it, and it stays inside. And you can take any two arrows inside, add them together, and guess what? The result is still inside. There are no gaps, you can't escape, it's closed, it's solid, it's convex.
And you know what? This quote from our source just hits the nail on the head. It perfectly explains why that two-ray example didn't work. Those two separate rays are what we call a union. And just like the quote says, the union of two cones might fail to be convex. It was that adding we did between the two separate parts that broke the rule and kicked us out of the set.
So, okay, we've got stretching, we've got adding, but why does any of this actually matter? What's the point? Well, it's because this seemingly abstract idea is the hidden engine behind some incredibly practical tools that get used every single day in the real world.
And this is where it gets really, really cool. I mean, think about computer graphics. The light from a spotlight or the field of view of a virtual camera, that's literally a convex cone. Or think about a massive logistics company trying to figure out the most efficient way to route thousands of delivery trucks. The math they use to solve that relies heavily on the geometry of cones. It's everywhere.
Now, one of the most useful types is something called a polyhedral cone. Just picture an infinite pyramid with flat sides. That's a polyhedral cone. And what makes it such a powerhouse is that you can describe it in two totally different ways. You can build it up from its edges, or you can carve it out of space using a set of simple boundaries. And having that flexibility is absolutely crucial for solving really complex problems in scheduling and resource allocation.
And that kind of brings us to our final thought for today. We started with two incredibly simple ideas, right? Stretching and adding. And from just those two rules, we built this whole concept of a convex cone, a tool that's used all over science and technology. It really makes you wonder, doesn't it? What other amazing, powerful ideas are out there, just waiting for us to discover the next set of simple, elegant rules?